Today we're going to talk about logarithmic equations. By the end of this video, you should be able to describe and graph a logarithmic function. First, we need to talk about the relationship between exponentials and logs. Last class we talked about exponential functions, and we had equations that looked like this. B was our base, and it was raised to the x power, and that gave us our y value. Logarithmic equations are the inverses of exponential equations. So if I take this equation and convert it to a logarithm, that would be log base b of y equals x. So the way that we read this statement is log base b of y equals x. So it's important to notice that a logarithm is equal to the exponent of the exponential function. And when you write the log, the b, the base, should be a subscript, meaning that it is lower and smaller than the word log and the letter y. So let's look at a few examples of converting between exponential and logarithmic equations. So first we have 5 squared equals 25. 5 is our base for our exponential function. 5 will also be our base for our logarithm. So we have log base 5. And then we know that the log has to equal the exponent. So this will equal 2. So log base 5 of 25 equals 2. Let's try another example. 10 cubed equals 1,000. Our base for this exponential is 10. That will also be our base for our logarithm. We know that this has to equal the exponent, which is 3. So we have log base 10 of 1,000 equals 3. If we have 8 to the 0 power equals 1, 8 is the base. So we have log base 8 of 1 equals 0, because it always has to equal the exponent. Let's look at one more of this type. We have 9 to the 1/2 power equals 3. So log base 9 of 3 equals 1/2. So you are allowed to have fractions when you do logs, that's totally fine. Let's look at a couple where we're switching from the log to the exponential. So we have log base 2 of 32 equals 5. 2 is our base, so 2 will be the base of our exponential. We know that whatever the log equals will be our exponent. So we have 2 to the 5th power equals 32. And if you're a little unsure of how to convert from a log to an exponential, the exponential that you end up with should always be true. If you type 2 to the 5th power in your calculator, it will equal 32. So you can use that as a way to check that you got the numbers in the correct place. And lastly, the last example here has log base 7 of 1 over 49 equals -2. So our base is 7, so we have 7 to the -2 power equals 1 over 49. So that is the relationship between exponentials and logs. We're going to use that to help us graph the logarithmic functions. But first, let's do a little bit more comparison between the graphs of exponentials and logs. Let's think back to inverse functions. We did inverses graphically at the beginning of the year. We did inverses algebraically at the beginning of this quarter. So an inverse function is a function that undoes another function. So how do we find an inverse algebraically? There were several steps, but you have to switch the x and the y. And how did we find inverses graphically at the beginning of the year? We took a coordinate point and switched the x and y coordinates. So we started with the point xy and we switched it so that it was the point yx. Or we could also think about reflecting over the line y equals x. So we're going to go back and continue to review what we did with inverses in the first quarter. We have a quadratic here. If we look at the domain and range of this quadratic, we know that all quadratics have a domain of all real numbers, or negative infinity to infinity. The range of this graph, this would be a parabola that is just shifted up. And so the vertex would be at 3. So our range is 3 to infinity. If we look at the domain and range of the inverse of this function, the inverse of this function, if we reflect it over the line y equals x, would be a parabola on its side. The domain of this graph would be 3 to infinity, and the range would be negative infinity to infinity. So you can see that the domain and range of an inverse are switched from the original function. So if exponentials and logs are inverses, we know that graphs of exponential functions have horizontal asymptotes. So what do you think graphs of logarithmic functions have? They have vertical asymptotes. So let's look at a few examples. The general equation for a logarithmic function is y equals a times log base b of x minus h plus k. So we're going to do this the same way that we did graphs of exponential functions. We're going to write out a, b, h, and k. For our first example, we have y equals log base 3 of x minus 2 plus 1. A is 1. B is our base, which is 3. H is inside the parentheses with the x, so that is 2. And k is the number being added at the end, which is 1. So, since exponentials and logs are related, we are going to use the related exponential function to help us find our points for our graph. So our base for this log is 3, so we're going to use the equation y equals 3 to the x to help us find our points. So last class we looked at this. We had the x values, -1, 0, and 1. And if we do 3 to the x, 3 to the -1 is 1/3, 3 to the 0 is 1, and 3 to the 1 is 3. Now, we know that exponentials and logs are inverses, and with inverses you switch the x and y. So if I'm looking for the t-chart for y equals log base 3 of x, I'm just going to switch the x's and y's. Just like with exponentials, my starting point is going to be the point hk. So I'm going to start at the point 2, 1. So I'm going to put a little x there. And I'm going to use this t-chart starting from my starting point. So I'm going to go 1/3 in the x direction and -1 in the y direction from this x. So it's about there. Then I'm going to go 1 to the right and up 0 from the x, and then 3 to the right and up 1 from the x. Now, we mentioned that logs have vertical asymptotes. Your vertical asymptote is always going to be x equals h. So for this graph, our vertical asymptote is going to be x equals 2. So then we can go ahead and draw our graph. Now, to find the domain and range, our domain will always be h to infinity. So in this case, it is 2 to infinity. And our domain and our range will always be all real numbers, or -infinity to infinity. If you want to check your graph on the calculator, you can go to y equals. Then to type in the log, you go to math, log base, and it gives you little boxes to type the base in. So it was log base 3 of x minus 2 plus 1. Now, the hard part about the calculator is that it's not very high resolution, so as it gets really close to the vertical asymptote, the calculator has a hard time showing that part of the graph. So it ends up making it look almost like a square root function. But you need to know that the graph will continue downward, approaching the vertical asymptote. It does not stop as it appears on the calculator. Let's look at a couple more examples. Here we have log base 1/2 of x plus 3 minus 2. So our a value is still 1, our base is 1/2, h is -3, and k is -2. So again, we're going to use the related exponential function to help us. So if we look at the exponential function y equals 1/2 to the x, and we make a t-chart for that function, 1/2 to the -1 power is 2, 1/2 to the 0 is 1, and 1/2 to the 1 is 1/2. Then if we switch the x's and the y's, log base 1/2 of x would have a t-chart 2, -1, 1, 0, and 1/2, 1. Our starting point remember, is hk, so for this problem it will be -3, -2. Remember that our asymptote is always x equals h, so we can go ahead and draw our asymptote in here. And then we can use our t-chart to plot these points from the starting point. So if we go over 2, down 1, over 1, up 0, and over 1/2, up 1. This graph looks a little bit different than the last graph because the base is 1/2. It looks like the flip of the previous graph. So for this graph, our domain is -3 to infinity, and our range is -∞ to infinity. One more example. We have 2 times log base 2 of x plus 5 plus 3. So a is 2, b is 2, h is -5, and k is 3. Again, we're going to find the t-chart for the related exponential function, which would be y equals 2 to the x. Two to the -1 is 1/2, 2 to the 0 is 1, and 2 to the 1 is 2. When we switch x and y to find our t-chart for log base 2 of x, we end up with 1/2 -1, 1, 0, and 2, 1 as our points. Since we have an a value of 2, we need to add another column and do a times y. So we need to multiply all of the y values by 2. It's important that you multiply by a after you have switched the x and y. Our starting point for this graph, remember, is always the point hk. So this will be -5, 3. Our vertical asymptote will be x equals -5. And then remember, we need to use the x column and the a times y column to plot our points, always starting at the starting point. So if we go over 1/2, down 2, over 1, up 0, and over 2, up 2. This one is stretched compared to our previous graphs. The domain for this, remember, is always h to infinity, so this is -5 to infinity. And the range is always -∞ to infinity. So make sure that you review the differences between exponentials and logs and how to convert between the two.